Hello, in this video we're going to talk about this question: how can we use quadratic functions to model real-life situations? In order to understand how we can use them, first we need to review a little bit about our quadratic functions. We have these three forms. This first form is called vertex form of a quadratic function. This next form is called standard form, ax squared plus bx plus c. And this last form is called intercept form because we have the two x-intercepts. From vertex form, we can easily find the axis of symmetry by setting what's inside of the parentheses equal to 0 and solving to get x. We use that axis of symmetry to get our vertex at hk. The next form, we can easily find where it crosses the y-axis, the y-intercept, by looking at the constant number c. And then we can get the axis of symmetry by looking at negative b over 2a. And then this third form, we get the x-intercepts by setting what's inside of the parentheses equal to 0 and solving. We get p0 is one intercept and q0 is the other intercept. And then here you can see that all of these intercepts and axis of symmetry and the minimum, maximum, increasing, decreasing can also be found by looking at the parabolas. And that's specifically what we're going to be talking about in this video. So we're going to be talking about the maximum when the vertex is at the top and the parabola opens down, the minimum when the vertex is at the bottom, the parabola opens up. We're also going to be talking about the x-intercepts, where the graph crosses the x-axis. So let's apply this understanding to some real-life situations. Our first problem here says an amateur rocketry club is holding a competition. There is cloud cover at 1,000 feet. A rocket is launched with a velocity of 315 feet per second. Use the function h of t equals negative 16 t squared plus v sub naught t plus s sub naught. So sub naught means the initial, the starting, before any time has passed. V for velocity, s for starting height. To determine how long the rocket is out of sight. Okay, so velocity, this 315 feet per second, literally gets replaced right here in place of v sub naught. So we're going to want to go over to Desmos and type this equation: h of t equals negative 16t squared plus 315t plus 0 because the rocket is being launched from the ground. Except when we plug it into Desmos, we really want x instead of t, x instead of t, x instead of t, and there's no need to type plus 0. When we do that, we start with a graph that looks like this that is absolutely unreadable. So let's change our settings by clicking on the wrench. We can change the y-axis, the x-axis very quickly here. I think I only want to change the y-axis. Its maximum height of 41 feet is clearly not tall enough. I can also add an x-axis label. And I can add a y-axis label. When I do that, I get this. I have my x-axis label is time in seconds. My y-axis label, I typed in height in feet above the ground. And then you can see my parabola goes up. I can see the vertex of it because I changed my y-axis to go high enough. And then I can see how long it takes the rocket to come back down to the ground. But wait, we're forgetting there is cloud cover at 1,000 feet. We need to add that into our graph. So we're going to type y equals 1,000 to represent the cloud cover right here. Now, some things that I know about my graph is I know that this vertex right here represents the time at which, 9.844 seconds, the rocket reached its maximum height of 1,550.391 feet. That's good, but it does not answer the question. I can also look down here at the x-intercept and see that the rocket landed at 19.688 seconds. That's how long it took for the rocket to come back down to the ground. So our real question is how long the rocket is out of sight. So to find out when the rocket is out of sight, what I really want to do is click here and click here so that I can see that the rocket enters the cloud cover at 3.979 seconds. And it keeps going. We cannot see this because it's above the clouds and we're below the clouds. And it comes back down at 15.709 seconds. It comes reappearing through the clouds, and I can use Desmos to subtract those 2 seconds, 15.709 minus 3.979, and that's going to be 11.73 seconds. So when I write this up, I'm going to make sure that I answer the question very clearly. The rocket disappears in the clouds at 3.979 seconds after launching and reappears at 15.709 seconds after launching. The rocket is out of sight for 11.73 seconds. So I used complete sentences. I said all of the numbers that I was using in my sentences in order to reach my final answer. Okay, let's look at this problem. We have a soccer player kicks a ball downfield. The ball starts on the ground and its height increases until it reaches a maximum height of 8 yards, 20 yards away from the player. So the 8 yards, even though it's listed first, it's actually the y because the height is what we're looking at. The height is y, and that's 8 yards. 20 yards away is going to be the x. A second kick is modeled by the equation y equals x times the quantity 0.4 minus 0.008x, parentheses. And our questions are which kick travels farther before hitting the ground and which kick travels higher. So those are good things to ask. So first, let's plot this point in Desmos. And I'm going to plot that point in Desmos by simply entering parentheses 28. And I'm going to check that I want to label it, and I'm going to type in maximum height. So I have my maximum height right here. And then I also went ahead and entered distance in yards on the x-axis and height in yards on the y-axis. Okay, I can type in y equals a times the quantity x minus h squared plus k, and I could use sliders, except I know that my maximum height, 8 yards, is my k value, and I also know that my 20 yards away is my h value. So that's going to reduce it so that I only have one slider. Okay, so here I have my equation, y equals a times the quantity x minus 20 all squared plus 8, and one slider. I can tell that when a is 1, the parabola opens up because a is positive. I don't want a parabola that opens up because a ball is not going to start in the air, come down, and go back up. A ball is going to start down here at a distance of 0 and a height of 0, go up, and then come back down. So let's move this slider right here so that our parabola opens down. Okay. To go from negative 10 to 10 is not sufficient. So what I really want to do is click in that, and I want to change this to go from negative 0.1 up to 0. I know that it needs to be negative. I'm going to make my step super tiny and call this 0.01. And when I do that, I can take this dot and slide it back and forth so that I can make this part of the parabola come back here over to 0, 0. Now I know that based upon my axis of symmetry going through the vertex, if it's going to go up and have a maximum height at 20 yards away, that's actually going to be reflected over, and it should match over here coming down at 40 yards away. But let's move the slider and find out. So we have right here, when we set a equal to negative 0.02 using the slider, just playing with it, we intercept the y-axis and x-axis at the origin right here at 0, 0 for distance and height, go up to a maximum height of 28, and come down, and we do indeed hit the ball. The ball does indeed hit the ground at 40 yards away from where we kicked it. Okay. We have a second equation. We need to enter that into Desmos. Y equals x times the quantity 0.4 minus 0.008x, close your parentheses, and that is this second parabola right here. So the first parabola represented the first kick with a maximum height at 8 yards in the air, 20 feet away, and it came down, or 20 yards away, and it came down 40 yards away when it finally hit the ground. The second player was really easy to graph. We plug that in and we find right here, we click at the vertex, a maximum height of 5 yards when the ball is 25 yards away. And then it finally reaches the ground again when it is 50 yards away. So we can use this information to answer our questions. Which kick travels farther before hitting the ground? We're going to look at where it comes back down to hit the ground, write ourselves some complete sentences using all of that information. The second kick travels 50 yards, but the first kick only traveled 40 yards. The second kick travels 10 yards farther before hitting the ground. And then the second question, which kick travels higher? We're looking at our maximum height for each one. The first kick reached a maximum height of 8 yards, but the second kick only reached a maximum height of 5 yards. The first kick went 3 yards higher than the second. And those are two problems about launching a rocket or kicking a ball. Thank you for watching.